In this video, I'll be talking about quadratic congruences with composite moduli. In my earlier videos, we have already discussed quadratic congruences with prime moduli. So let's continue now the results with the composite moduli. So the theorem speaks let n is equal to this prime factorization as mentioned here. This be the prime factorization of a positive integer n strictly greater than 1 and the GCD of a and n is equal to 1. Then x square congruent to a modulo n is solvable if and only if the Legendre symbol a by pi is equal to 1 for each I varying from 1 to r. And the second condition says a is congruent to 1 modulo 4 if 4 divides n but 8 does not divide n, and a is congruent to 1 modulo 8 if 8 divides n. Now to prove this theorem star, I'll first prove this theorem number 1 and theorem number 2. And here you can see that this theorem 1 and 2 cover all possible values of the number capital N. Let's say n is equal to 2, the composite number, all the 2 is a prime, so we'll start it from this. So let's see here in the theorem number 2 first part, we are talking about moduli 2. When n is equal to 2 square, so this means we are talking about 4, which is here. When n is equal to 2 cube, or we may take when n is equal to 2 to the power n is greater than or equal to 3. So these cases are then covered over here in the third part of theorem 2. And this has a solution when a is congruent to 1 modulo 8. So this address to this condition in the main theorem. Also when n is any odd prime to the power k, so and k can be greater than or equal to 1. So this is the case that I will be covering in theorem number 1. Once I prove this theorem number 1 and 2, this theorem star automatically follows. We can see that we want to find the x square congruent to a modulo n solvable or not. So let n is equal to 2 to the power k, p1 to the power k1, this was the prime factorization given to us, and pa's are distinct odd primes. So solving x square congruent to a modulo n is equivalent to solving this system of congruences. So this is same as the first congruence. I can simply write n naught as 2 times k naught. So that is written as a modulo n naught. And this is same as a times modulo n1. So I'm just giving the name as n1 as p1 to the power k1 and so on. So this congruence will become modulo nr, where so on nr is equal to pr to the power kr. Now this is same as system of congruences, and this I can again apply Chinese remainder theorem concept because each ni and nj, they are relatively prime. So hence we can solve the main quadratic congruence. Now the question is that individual congruence is solvable or not? So when I talk about individual congruences, this means it is 2 to the power k. So when it is 2 to the power k, this is our theorem 2, and when it is individual p1 to the power k1, this is what I can get it from the theorem 1. So by proving theorem 1 and theorem 2, I can get the result of theorem star. So now let's prove theorem 1 and theorem 2. So now we'll prove theorem 1, and in this case we can see the condition is if and only if. So let's start first from this condition that the congruence x square has a solution. So let's consider this case. Given x square congruent to a modulo p to the power n is greater than or equal to 1, this has a solution. And if this has a solution, this has a solution of course for all particular values also. So x square congruent to a modulo p to the power 1 also has a solution, because in that case I have considered n is equal to 1. And this automatically implies by definition that the Legendre symbol a by p is equal to 1, because it is solvable. If it has a solution, it is solvable, and by definition we know that the Legendre symbol value is 1 if x square is congruent to a modulo p is solvable, and in the other case this value is -1. So -1 otherwise. So one-sided proof is obvious. Now let's prove the otherwise. So conversely, we have been given the Legendre symbol a by p is equal to 1, and I want to prove that x square congruent to a modulo p to the power n has a solution. And we will prove now this converse part by induction, and in this case let's take n is equal to 1. If n is equal to 1, then x square congruent to a modulo p to the power n becomes p only. And as we have already said that the Legendre symbol a by p is equal to 1, this implies x square congruent to a modulo p, this is solvable, and if it is solvable, it has a solution. So for 1, this result is true. So for n is equal to 1, result is true. And now I'll take by assumption that the result is true for n is equal to k, and we will prove for k plus 1. So by induction step, we'll assume that the result is true for n is equal to k, and hence x square congruent to a modulo p to the power k has a solution, and let's call the solution as x naught. and I just simply substitute x naught in the congruence. So this gives me x naught square is congruent to a modulo p to the power k, and hence I can write this equation into equality. For some b, this will hold, x naught square equal to a plus b into p to the power k. And now we want to prove the result for n is equal to k plus 1. So as we proceed for proving the result for n is equal to k plus 1, let's recall the sum of the steps that I have done in the starting of the quadratic reciprocity law videos. What we have done is that if we want to solve a general quadratic congruence, which is ax square plus bx plus c is congruent to 0 modulo p, and here a is not congruent to 0 modulo p, so that it is quadratic congruence, and if a is congruent to 0 modulo p, this will actually become a linear congruence. So now considering that a is not congruent to 0 mod p, I can then multiply 4 times a onto both sides, and of course p is odd prime here, p is odd prime. So when I multiply 4a on both sides, this is the expression I get. This is congruent to 0 modulo p, where the GCD of 4a and p is also equal to 1. Now I can again rewrite this equation as 2ax plus b whole square congruent to b square minus 4ac modulo p. And I have renamed this quantity as y square. This side I have renamed as d modulo p. So we can say that y is 2 times ax plus b, and discriminant d is b square minus 4ac. So basically this quantity means that we want to solve something here in terms of moduli p, and d is the discriminant which is b square minus 4ac modulo p. This is what we have considered. Now you notice here that this quantity is coming as a linear congruence which is associated with this quadratic congruence. Now we are trying to solve the quadratic congruence of this type, and in addition to solve this, we always want to construct a linear congruence, so that from here we can come back to the solution of this one, and hence from here we can come back to the solution of our main quadratic equation. So now following this construction step, we first solve the linear congruence of the type 2x naught y is congruent to minus b modulo p. We can see it here, we can just compare it from here and we know it. We have already obtained a solution x naught here, and let me to call this equation number as equation number 1. I am going to use the same solution that we have obtained and substitute that solution here and construct a linear congruence something like this. This is 2 times x, and instead of this a, assume this as y, this is congruent to minus b. So if I can solve this congruence, this side, right hand side, so solving above linear congruence, and we know why this is solvable. This is solvable noticing that 2 times x naught and p, this GCD is equal to 1, because p is an odd prime here, p is an odd prime, 2 times x naught is an even quantity, so this GCD is equal to 1. So obviously this linear congruence can be solvable because the GCD is 1 and 1 divides this quantity b. So this is solvable, and let's say the solution is y naught. Now I want to use my previous equation 1, that is the x naught that has been constructed in this equation, and the y naught that have now is the solution of this linear congruence. So I am going to construct again an integer x1, which is x naught plus y naught into p to the power k. Now this acts as the solution of our congruence, desired congruence. So squaring both sides, we get x1 square. This is equal to x naught plus y naught into p to the power k whole square. This is same as x naught square plus y naught into p to the power k whole square plus 2 times x naught into y naught into p to the power k. I've just opened it as a plus b whole square, which is a square plus b square plus 2ab. Now this quantity is same as x naught. I have already obtained the expression for x naught in equation number 1. You can see that x naught is already given in equation number 1. Just substitute this value x naught here in this given equation. So this will become a plus b times p to the power k plus, let me to write this expression first, 2 times x naught into y naught into p to the power k plus this expression I am writing at the end, y naught square into p to the power 2k. A plus, let's common p to the power k on both sides. This will become b plus 2 times x naught y naught into p to the power k plus y naught square into p to the power 2k. And we can see that this quantity is coming with the power with the term p to the power k. Both terms are involving p to the power k. And also you can note it down that p divides b plus 2 times x naught y naught from the equation number 2. So this means this quantity is something a plus this expression is divisible by p. So let's call this as p times q into p to the power k plus y naught square into p to the power 2k. So we can see that we got a plus q times p to the power k plus 1 plus y naught square p to the power 2k. And now I can write this whole expression in the moduli condition as desired. So x1 square is equal to x naught plus y naught p to the power k whole square. This is congruent to a modulo p to the power k plus 1. So now it is clear, and obviously noticing that this quantity is greater than k plus 1, so I can just replace this is already in the moduli condition of p to the power k plus 1, and hence this hold the induction step for k plus 1. Now in the power we already have k plus 1, so we can see that for this value of x1, whenever I choose x naught plus y naught p to the power k, the congruence is solvable, and hence result is true for n is equal to k plus 1, and by induction it is true for all positive integer n. Now let's solve this quadratic congruence, and I'm going to follow the same step that I have followed just in the theorem. So to solve this case, because it is 7 square, or it is like p to the power k, and here to solve this I have to take one less power. So let me to first solve that x square is congruent to 23 modulo 7, and from there I am going to reach to the higher power. This result is same as if I solve this quantity is congruent to 2 modulo 7, because 23 minus 2, that is 21, which is divisible by 7, and I can see that 2 by 7 this value is equal to 1. So obviously a solution exists, and we know 2 by 7 is equal to 1, so a solution must exist, because we know the result that 2 by p is 1 if p is of the form 8k plus minus 1. So here this 7, we can see that 7 can be written as 8 into 1 minus 1. So considering this into mind, we know that the solution exists. So obviously x square congruent to 2 modulo 7 has a solution, and we can see that x naught equal to 3 will act as a solution. 3 square, that is 9, minus 2 modulo 7 hold a solution. And then from the theorem equation number 1, I can see that x naught square is equal to a plus b into p to the power k. This expression will hold. So this becomes x naught square, and x naught we have found it as 3 square, that is 9, and a in this question is 23, because this is what we are trying to solve, plus b we need to find into p to the power k. Now this was one step before that if we wanted to prove the result for k plus 1. So in this case, because we want to prove the result for 7 square, so I'll consider now this as 7 raised to power 1. So this expression means, or I may say 9 is equal to 23 plus b into 7. This result should hold for some b belonging to integer, and by looking at this expression we can directly say that 23 plus minus 2 into 7 will hold the result. So we know that what is b? B is equal to minus 2. Now once we have selected b, so that means we can now move equation number 2 in the mention in the theorem. So what is equation number 2? That was 2 times x naught y is congruent to minus b modulo p should have a solution. Let's substitute these value here. 2 times x naught value is 3 into y, which is congruent to, we have already obtained the value for b, that is minus of minus 2 modulo p. So this means 6y is congruent to 2 modulo 7. Now I need to solve this value here. This p is 7. Now I need to find a solution from here, that y naught. So by substituting the value of y naught, say y naught is equal to 1, it doesn't hold, y naught is equal to 2, this congruence doesn't hold, y naught is equal to 3, and so on. We find that y naught is equal to 5 gives the solution of this case, because 6 into 5 is 30, minus 2, 28 is divisible by 7. So now by theorem we know what is x1. x1 is x naught plus y naught into prime, because we have already here to the power 2, so take one less value, and in this case x naught is 3, y naught is 5, and the value for prime is 7. So that will become 3 plus 35, this is equal to 38. So x1 equal to 38 act as a solution of our given quadratic congruence. So as x1 equal to 38 is one solution, let's find the other solution. In the other solution we have 7 square, that is p to the power square, the given prime, minus 38. So this value is 49 minus 38. This gives me the value as 11. So the other possible solution is 11. Or we can say x1 square is congruent to 23 modulo 7 square. This has a solution as x1 equal to 38. So we know that minus 38. So if we take, because x1 square we have, so even if we take x1 as minus 38, and we can see that this is congruent to 11 modulo 49. So from here also we can directly see what is the other possible solution. So either we can look at from here, or you can look at directly from here. Just put it that's congruent to 11 modulo 49. Now suppose we want to solve this quadratic congruence x square congruent to 23 modulo 7 cube. Now you can see that in the previous example I have taken here as 7 square and here it is 7 cube. So again, to start we need to consider one previous congruence power. So I need to consider the solution of this 7 square, and that means to solve this I need to further consider the previous congruence, that is x square is congruent to 23 modulo 7. So hence from the previous example I already know what is the solution in this case. So and hence I have found the solution for this case. So that means for this case I can, keeping in mind the previous example, I can start the solution x naught equal to 38 for this congruence. And so first I will use this x naught to find the value for b. So this means x naught square is equal to a plus b into p to the power k. So this power k should be taken 1 less than in this case. What is a here? This is 23 plus b will need to find it out, p square, that is 7 square, because to find 7 3 I have started finding the solution of 7 square, that I already found, that x naught equal to 38. So this value is 38 square, and solving this equation we know what is the value for b. So b is equal to 29, or I may say 38 square, this is same as 23 plus 29 into 7 square. This equation holds. So we know what is now the value for b. Once we know what is the value for b, now I can construct the linear congruence. Linear congruence is 2 times x naught into y is congruent to minus b modulo p. This means it is 2 into x naught is 38, y we need to find it out, minus 29 modulo p. This value is 76, y is congruent to minus 29 modulo p, and in this case prime is 7. So you notice here it is p to the power 1, whichever prime that we are discussing, and in this expression here whenever we are constructing in this expression, this power is 1 less than what is desired in our question. So we can say that this congruence has a solution, y naught equal to 1 is the solution. So once we have found y naught 1 and we have found the x naught, we know that the congruence which is given to us, x square is congruent to 23 modulo 7 cube. This is satisfied by x1, which is equal to x naught plus y naught into 7 square. We know what is x naught, that is 38, y naught we have found, which is 1, 7 square 49, so 38 plus 49, that will become 87. So x1 equal to 87 act as the one solution. One solution we have already found, so just take negative of that. Minus 87, this is congruent to 256 modulo 7 cube. So that is act as the another solution. Now let's prove the theorem 2, where I have moduli 2, moduli 4 and moduli 2 to the power n greater than equal to 3. For the first case, this result is obvious. When we say that x square is congruent to a modulo 2, this always have a solution, and it is true. Whenever I take x is equal to some odd value, say for example 2k plus 1, so this means x square, this value will become 4k square plus 1 plus 4k. This means this value is 4k square plus 4k plus 1. Now whenever we have this plus 1 and here a is an odd integer, so for every odd quantity we get a solution. So this is always solvable. This is always solvable, and hence it has a solution. So the first result hold trivially. In the second result, what I want to prove is x square is congruent to a modulo 4 has a solution or not, and in this case it says a is congruent to 1 modulo 4. So we know from this result only that square of any odd integer is congruent to 1 modulo 4. So this means whenever this is congruent to 1 and on this right hand side we have a, which is an odd integer, this will have a solution. So this means consequently this will hold whenever a is congruent to 1 modulo 4. So this result is if and only if, obviously, if a is congruent to 1 modulo 4, this has a solution, or we say whenever this have a solution, this has to be a is congruent to 1 modulo 4. And also in the reduced class, x equal to a and x equal to 3 act as two solutions. Now let's prove the third part, and in the third part I want to prove that x square is congruent to a modulo 2 to the power n greater than or equal to 3 has a solution if and only if a is congruent to 1 modulo 8. So let's start from the other side first of all, and we see that square of any odd integer, this is congruent to 1 modulo 8. So this way we will prove this result, and we can see that because consider any odd integer, say for example x is of the form 4k plus 1 and 4k plus 3. So we have considered odd integers. Take the square of these 4k plus 1 square, this will give me 16k square plus 8k plus 1. So we can see that this is 8q plus 1. So it is of the form 8k plus 1, and similarly 4k plus 3 whole square, this will become 16k square, and then we have 24k plus 9. So this means it is 16k square plus 24k, and 9 I can write it as 8 plus 1. So this From here I can take 8 common. This is q plus 1. So again it is 8k plus 1 form. So this way result is obvious that if this has a solution, then a must be congruent to 1, because we are saying x square is congruent to a modulo n has a solution. So whenever we have an odd integer, this condition is automatically satisfied. Now let's prove the other way side, and in the converse I'll prove again by induction. And for the first step in the induction, I need to consider n is equal to 3, because the least possibility that we are working is with the n greater than or equal to 3. So the least value n can take is 3. In this case, the congruence x square congruent to a modulo 2 to the power n, or I can just replace this value as x square congruent to a modulo 8. This is solvable if x can take value 1, 3, 5 and 7, and that satisfy this congruence. So that means the result hold true for n is equal to 3. And by induction hypothesis, suppose that the result is true for x square congruent to a modulo 2 to the power n, and this has a solution, and let's call the solution as x naught. So in this case I may have x naught square equal to a plus for some b into 2 to the power n. This will hold. And notice here that x naught is an odd integer because a is odd, and here this expression, this is b into 2 to the power n, and we know that n is greater than or equal to 3. So that means this expression is even, but a is odd, so the total quantity on the right hand side must be odd. So this means x naught is an odd integer, so that the net result makes meaning. So here we can now consider a linear congruence, and for which we want to find the result as we have applied in theorem 1. But remember, in that case we have considered the linear congruence as 2 times x naught into y congruent to minus b modulo p, where p is odd prime, and we see that 2 and p have the GCD 1. So now in this case we only consider this much expression, we do not consider 2 because it is already inside the modulus. So we just consider that x naught y is congruent to minus b modulo p should have a solution. This has a unique solution again because the GCD of 2 and x naught is equal to 1. We have just proved that x naught is odd, and so we can find the y naught. Once we have found y naught and we already have found x naught, so we can construct the integer x1 as we did in the previous case. This is x naught plus y naught 2 times to the power 1 less than expected. We want to prove the result for 2 to the power n, so here you just consider 1 less powers. And now we claim that this satisfy our congruence for the next step. Now we claim that x1 satisfy x1 square congruent to a modulo 2 to the power n plus 1, and this will complete our induction step, and that's the last induction step. If we can show that the x1 that has been selected from this case is satisfying this congruence. So just square on both sides, we can just notice that x1 square is congruent to x naught plus y naught 2 to the power n minus 1 whole square. This is equal to just applying a plus b whole square formula again. So this will become x naught square plus x naught y naught into, of course, 2 to the power n because of the 1 2 that is going to come in 2ab formula, and then we have y naught square into 2 to the power 2n minus 2. This value is same. Now we have already assumed what is the x naught square value from here. Just substitute this value again in this equation as we did in the previous theorem. So this will become a plus b, and here this is 2 to the power n. So just club that value with the other expression. So it will become b y naught into 2 to the power n plus y naught square into 2 to the power 2n minus 2. Now I can again write this expression as a plus b plus x naught into y naught into 2 to the power n plus this value I can write it as y naught square into 2 to the power n plus 1 plus n minus 3, which is equal to a plus 2 into q into 2 to the power n plus y naught square into 2 to the power n plus 1 plus n minus 3, where this expression I have written here from this case. Let's call this as delta. We know that 2 divides, so from here I can just write it down that 2 divides x naught y plus b. So this is the same expression that I am writing, and this expression is true for a particular value y naught that we have claimed that there exists a y naught for which this solution holds. So 2 divides x naught y naught, so that is replaced by 2 times q naught into y naught. So this is further congruent to a modulo 2 to the power n plus 1. Now because in both the expression we have 2 to the power 1 and then we have n, so this makes n plus 1, and here already we have n plus 1. So this congruence hold x1 square is congruent to a modulo 2 to the power n plus 1 as desired. So our induction step is complete, and hence we prove the theorem.